This is the next video in a chapter on advanced theories of bonding. I know you feel concerned that we're moving on to a new section of hybridization when we didn't finish the third facet of valence bond theory. Never fear, orbital energy, that third facet will fall under this category. So we're going to take a step back and we're going to look at what we've learned so far about valence bond theory in its current version and how well that matches up with the experimental evidence and VSEPR theory about geometry of molecules. Because after all, what we come up with as our theory does need to make sense with experimental evidence. So let's look at the water molecule, which we're all familiar with as an example. When we draw the Lewis structure for water, it looks something like this. And when we have the valence bond theory and we use that to try and explain this theory, we end up with something like this. We know oxygen is in the center, and we know there will be a hydrogen to each side of it. And we need to choose an orbital that each atom is going to use to overlap. So hydrogen only has one orbital, so it's pretty clear which one we're going to choose for that. We're going to have the 1s orbital for this hydrogen and the 1s orbital for this hydrogen. And then we need to choose orbitals from oxygen to overlap with each of those hydrogens. And we learned that we want to pick an orbital that overlaps with this internuclear axis for each of the bonds. So why don't we go ahead and pick a p orbital for each of these? So we'll do a p orbital on this axis to overlap with the hydrogen on the left. So that'll be our oxygen 2py orbital. And then we can do another p orbital on this axis, our 2px orbital, to overlap with this hydrogen. And just to make sure that it doesn't look like that's a d orbital, let's outline this one in green. There we go. So according to this model, if we used 2 p orbitals from the oxygen to do the two overlaps, we know every p orbital is 90 degrees apart. So the angle between the hydrogen, oxygen, hydrogen would be a 90-degree angle. Now, does this match with what we know to be true from experimental evidence and VSEPR theory? Well, we learned in VSEPR theory that oxygen is connected to 2 hydrogen atoms, and it's also connected to 2 lone pairs. So it has 4 electron groups, making it a tetrahedral structure, and tetrahedral structure have bond angles of 109.5 degrees. So this is the correct model. Experimental evidence shows that the actual angle between these hydrogen atoms is 109.5, but our current valence bond theory predicts that it was 90 degrees. So we're going to need to add some more to this theory because clearly we're falling short of predicting what the real geometry looks like. So we need to expand this theory. And we're going to expand it with hybridization. Hybridization will help to modify the orbitals we have as options so that we can make our picture look like this VSEPR picture, but with orbitals drawn on each atom. So that brings us to the third facet of good orbital overlap, which is having appropriately matched orbital energies. So the oxygen in our water molecule has 4 electron groups around it. 2 of them are bonding pairs, and 2 of them are lone pairs. So the oxygen needs 4 atomic orbitals to hold them, and those orbitals need to have the same shape and the same energy. And we have a fancy word for having the same energy, meaning they're degenerate. So we need orbitals that are degenerate with the same energy and that have the same shape to hold those 4 groups. That's the lowest energy orientation, is to have 4 matching orbitals. So how are we going to get 4 orbitals of the same energy and the same shape? An s orbital and 3 p orbitals are most definitely not the same shape. We are going to have to put those orbitals into a blender, mix them together, and spit out 4 identical, slightly differently shaped molecules. And that process is called hybridizing or hybridization. So what we're going to do is we are going to blend the atomic orbitals together. On a bonded central atom. And we are going to make from those new orbitals that we'll call hybrid orbitals, because they're a combination of several different kinds of orbitals. So let's talk about what features we can expect to see in these new orbitals called hybrid orbitals. You thought you knew everything about orbitals, but there is still more to learn. So features of hybrid orbitals. So hybrid orbitals only exist on bonded central atoms. So we don't need to worry about hybridizing on terminal atoms because they're only bonding with one other thing, and they can pick whichever orbital they like. They can pick out the best one for that bond. The number of hybrid orbitals that we're going to make is going to be the same as the number of electron groups around that central atom, because we're trying to make one orbital to hold each of those electron groups that is equal in shape and in energy. The number of hybrid orbitals that we make is also going to match the number of atomic orbitals that we mix together in the blender to make them. This is a feature of group theory. The number of things that you put in is going to be the same as the number of things that we put out. So we're going to blend together a certain number of orbitals, and we're going to make the same number of new orbitals. Other features, they will have the same shape, all of the hybrids that we make. All of the hybrids will have the same energy as the other hybrid orbitals in the set. And when we form these hybrid orbitals, we are only going to use them to form sigma bonds. These are going to be excellent choice orbitals that lie on the internuclear axis. And so we are going to use them for the high quality, strong, single first bond in each bonding pair. So in the next video, we will talk about the first kind of hybridization, which is sp3 hybridization.